Welcome back in the course of higher surveying, and today we are in our last module, module 10, navigation. We have used this term navigation many times. For example, air navigation, sea navigation, space navigation, satellite navigation, ship navigation, road navigation, and so on. Well, what's the meaning of the navigation? I gave you one example in module 2. We discussed about a particular case of moving from one point to another point. You wanted to celebrate some event with your friends in a famous restaurant in your city. However, you do not know how to reach there. To reach at the restaurant place, what do? You use your smartphone, and in the smartphone you have an application or app called Map. So in the map, GPS is showing your location where you are currently located. Next, you try to put a query where you put the name of the restaurant and you locate it, and then we say navigate. By putting the navigation option, what do you have? You have the complete path of the restaurant from your home through the city, and then you start to move on that path. What happens? GPS is continuously marking your position on the background map of the app. Suppose you get deviated from the course, so GPS shows you where you are exactly at a given moment. Realizing that you are deviating away from the course, so what do? You use your brain, or you use a control. Your brain is like a control system here. So it controls you to go back to the course. So once you get on the course, again you will start following a certain direction so that you remain on the course. So we use the word navigation. So what is the exact meaning of the navigation? Is it different from the mapping or traversing? In this lecture, we are going to discuss about the navigation. I would like to confirm here that the navigation is the science that uses most of the technologies that we have discussed before. By those technologies that we have discussed, we prepare a map, and ultimately navigation uses the map at the background and some kind of sensing device like GPS to locate your current position. I hope I have given you enough hint. So let us go to the lecture on navigation. Today we have our module on navigation, and it has only one lecture. And these are the books. I would like to highlight here that the first book is easily available, and the second book is about GPS. The third book and the fourth book written by the same author. Fourth book is little old. You may get third book, which is published in 1983. So again, I request you to go to some library. Perhaps books are little expensive. So what is the navigation? I have written a formal definition over here. If you read it carefully, so it is guidance given to move an object from one known point to another known point in a reference grid. So what is the meaning of each and every point? Guidance means you are giving a guidance, or you are controlling the object from one known point. The first point is known, as well as the next point is also known to me. So both points are known. Now I am giving the guidance to the object that how to move on a certain path such that it will reach to the another known point. Basically, I am initiating on a track or on a course between the two known points. And again, we are using a word reference grid. Remember the example of the module 2 where we talked about the map projection, and we said that we are going to use the 2D map projection of spherical Earth. The accuracies are not that critical in case of navigation. However, the process of navigation is very critical. For example, aircraft which is landing at the airport, some error of 5-10 meters in its position can be acceptable to the pilot, because pilot is using some visual devices to land there. Similarly, if you are reaching to a restaurant, 4-5 meter error is also fine, because you are very close to the restaurant, and again you do not want a pinpointed location. So your purpose is to reach very close, not exactly at a certain point with centimeter level accuracy. Similarly, if there is a ship that is navigating from one country to another country across the sea, if the land is visible from a couple of kilometers, it's absolutely fine. So this is the kind of understanding we should have, that there is a relevance of the reference grid or the 2D map projection. Then there is a one known point and there is another known point, and the moving object has been given the guidance, and that is called the navigation. So what is the process of navigation? Here I have written the process of navigation in the steps. You can read it yourself. I am going to explain it in the next slide. Let us say the same example, you want to go to a restaurant. In the grid system or 2D map projection, the restaurant is located here. You have the application that gives you the path from home to restaurant. Let us say it has given you some path like this. GPS is showing that you are somewhere here and now you want to reach here. Let us say this direction on the path. GPS is showing your correct path like this, like this. If you are moving on the course, for example, you get deviated from somewhere like this and somewhere here now. So what happens is your brain works as a control system that says you immediately reach to the course here, somewhere on the course. So you may go here or you may go here, but anyhow you will try to reach to the course. Okay, let us say again you have reached here. So GPS is again showing you this position and you keep on continuing like this. So all these positions shown by the GPS dynamically with time. By following this path you reach to the restaurant. So all these are GPS positions. So I can say here that your position is changing with the time. Some of the important terms, this term we call the course. Remember, the restaurant is known point and home is also the known point. So the course can be known or can be unknown. But generally when we use some applications like mobile application, it gives you some path which could be shortest or maybe slightly longer than the shortest one. But it gives you some path, and that is why I should know what is the exact path. If path is not known, we can do it on the fly also. And that kind of options are on the fly navigation. So that's the process here. What do you do basically? We place an object on the course somewhere at a known position. Let us say if I place at this location x, y and z, or call it x1, y1, z1. From this point, we are starting directing or guiding the moving object in certain direction. Let us say this direction. So the next point, again the direction changes. So we keep on continuously guiding the object. In case of human being, in the example of home to restaurant, what is the control system? Your brain is control system who is guiding you. So we are using some kind of artificial brain, or we use the artificial intelligence to control the vehicle or the moving object. I hope you got the idea. So in the process of navigation, you place an object on a course. That means already 2 points are known to you. You have decided a course. You place the object on a course at the known position, and from that known position, you start guiding the object in a known direction. And from that, you try to estimate the next position of the object, and based on that information, again you guide it. The process of control is also there, and that is why you can see that the navigation process requires the control system in some way. It could be an artificial control of machine, or it could be a natural brain control of a human being. But we need some kind of control system, and that is why this topic of navigation is also considered in a detail by the control system subjects or the courses. Well, you can also read about navigation in the control system books. Let us go ahead. So what are the modes of the navigation? The first mode is on the land. That means we travel by train from one known point to another known point. Let us say from Patna to Banaras. Both points are known to us, and there is a track between the two places. The train is moving. Well, that's a perfect example of a navigation. So train is navigating from Patna to Banaras. Similarly, the navigation by road, I have given you example of the restaurant. Then navigation in the air. Navigation in the air can be by aircraft, or we are trying to send the missile from one point to another point. Remember, both points are known. Sometimes when we launch the missile, you may say that one point is known from where we launch, however, another point is not known. No. In fact, we know beforehand that where is the exact point where we want to bring or we want to put the missile on. And that is why again we use the track between the 2 points, and we want a certain track that missile should follow. And that is why the word missile navigation came. Then we have drone or UAV navigation. When we fly the UAV, what happens? A drone moves from this way, it comes back on another track, it moves on the parallel tracks, and finally it reaches to some known point, let's say exit point. Same thing happened in case of airborne mapping. We have an aircraft and it also moves on the parallel lines in case of LiDAR, photogrammetry. Similarly, we have the space navigation or the satellite navigation. We can also see here the navigation in the space. That means when we launch a rocket, what do we want? We want to place one satellite in certain orbit. So what happens is rocket is launched. So once it goes in certain orbit, rocket detaches the satellite and satellite is placed in that orbit and satellite starts moving on certain track. Satellite is moving or satellite is navigating. First the rocket was navigating from point on the earth to the certain orbit point, and thereafter the satellite starts navigating in certain orbit because the orbit is known. When we know the elliptical orbit of satellite, that means I know each and every point. If I am measuring the position of the satellite on the orbit, I am trying to track it. In case of GPS, the master control station tracks GPS satellites whether they are moving in the designed trajectory or not. Once they are away from the trajectory, there is a control system that brings them to the trajectory again. If they move away from the trajectory, again brought back to the trajectory. And so we have some kind of path around the designed trajectory. Now you can understand that how control system is playing a big role here. We have the navigation in the sea where we are having a ship or boat. In another case, we may be having a submersible that is moving under the water from one point to another point. What about the divers? We have divers, they do the underwater shooting. Do they know the point? In fact, they know the point from where they start and end their work. However, if they do not really know what's the end point, they are taking a big risk. So rarely divers do this job. They generally know from where to start and where to end. Then ROV navigation. ROV is like UAV. UAV unmanned aerial vehicle, so it moves in the air, and ROV is remotely operated vehicle which moves under the water. So they are basically automatic vehicle that is used to detect or search under the water, maybe sea or river. There is another classification, the geodetic navigation and the local navigation. What is the geodetic navigation? If I have a global reference grid system, that means let's say WS84, or I am using some map system, maybe LCC projection or UTM projection, having some global grid like WS84 or Everest, it is called global navigation. On the contrary, we have local navigation. What is local navigation? Suppose in this room, I am having a robot and I want to test my robot whether it works the way I want. So what will I do? I give instructions to my robot that it should move from this point to this point on a certain course or track. So once robot starts, we keep on controlling it and try to see whether it performs well. So in this case, the map of my room is enough for this purpose because I just want to test robot. So that's local navigation. In your locality or colony where you're staying, suppose you celebrate an event, for example, some kind of party or some kind of public event like festivals like Diwali or maybe Christmas or maybe 31st December, New Year evening. So what do you do there? You try to bring some people from this point to this point. So in that case also your concern is all about the local place, and that will be the example of an local navigation. I hope you got the idea. So let us classify the navigation systems. Basically, they are classified in two categories. One is row-row navigation or row-row-row navigation, or sometimes they are called the circular navigation. And then other mode is hyperbolic navigation. Let us look into what is circular navigation and what is hyperbolic navigation. In case of row-row navigation or row-row-row navigation, row represents the range. Remember, we use the word row to represent the range in the survey engineering, and that is why it is called row-row navigation. So what's the meaning here? Let us say there is a transmitter here and it is transmitting the signals. The wavefronts are like this. And there is another transmitter here, let's say T2, and it is also sending the wavefronts or pulses. So now I can find out the intersection of these two pulses or the wavefronts. If I say that distance here from point T1 to the point A is equal to R1 or rho 1, and from T2 to A is equal to rho 2, and at certain time T I am measuring it using this combination of rho 1, rho 2 and T, I can find out the position of point A. Since I am measuring two ranges, it is called the rho navigation. In case of 3D systems where I am measuring 3 ranges with time, so I have 4 measurements, time, 3 distances, rho 1, rho 2, rho 3. So that is called the rho navigation. We can see here that in case of rho navigation, we need 2 transmitter or 2 devices. On the other hand, I can also say that the point A where object is there, it could also send the signals, and signals are received by these receivers. So both things are same, only the location of the transmitter is changing. So both are example of rho navigation. Now you can imagine that GPS is an example of the circular navigation, or it is a rho navigation. We measure the distance of the receiver on the ground surface from couple of satellites. So the rho is the range between transmitter and the moving object, or between the receiving object and the transmitting object. Please note that time of flight, or it could be the phase difference measurement, both are used in case of rho navigation. Two distances from moving body to two transmitters or two receivers are estimated. So intersection of the two ranges or the range circles give the position. Here I would like to tell you about the local navigation. Sometimes we also use the word positioning instead of local navigation. Positioning does not mean to determine the position only, and that is why for local area navigation, where position is much more important, as we have already said that sometimes along with the direction of movement, position is equally important in navigation. That is why we are determining the position of the moving object. Minimum 2 transmitters are needed, or we can say minimum 2 receivers are important. Let us say if there are more than 2 receiving objects which are fixed on the ground surface, or there are 2 transmitters fixed in the ground surface and object is moving. There are more than 2 fixed objects which can receive or transmit on the surface of ground. What will happen? The moving object has a choice which 2 objects the signal interaction should be done, and that gives the flexibility. That means whether I take the AB or ABC or BC or C and A out of 3. If I take such objects into consideration, what will happen? That accuracy of the moving object will increase. So that's the advantage here. What's the disadvantage? I need to have a stable time clock, because the range is measured with the help of time difference only. So the time of travel is basically converted to the distance or rho, and that's why the stable clock is very much important here. So any drift in the clock affects accuracy. Moreover, accuracy is a function of geometry of the network that we are making with the object on the ground surface and the object that is moving. The geometric dilution of precision concept comes from here only. Now let us look into the hyperbolic navigation. Let us say there are 2 transmitters shown by the red plus sign and the black plus sign here. Transmitter at black plus sign is sending some signals. So these are the wavefronts like this. These wavefronts are moving in the space with different multiples of wavelength. So as it reaches to larger distance, it has covered some multiples of a wavelength. So let us say 2 lambda, 3 lambda, 4 lambda, 5 lambda, 6 lambda and so on. Now you can see here that these are the wavefronts created by the transmitter shown by the black plus color. Similarly, there is a red plus sign transmitter, so it is also sending the pulses like this. By the interaction of these pulses, we can find out the position or the intersection point. That means if object is moving on that certain point, I can find out this location by the solution of the 2 such circles. Should I call it the circular method? No, because there is a small gap here. What is the gap? So let us look into that. So let us see, there is a line here which is connecting 2 points. This line is called the baseline. Similarly, if there is a line here, that is a center line. From the center line, each of the transmitter are at same distance, which means if the two transmitters are sending the pulses at the same time, they will have equal range or equal diameter of the wave fronts at the center line. However, if we place the object other than the center line or baseline, what will happen? Let us say this point, it is 2 lambda, 2 lambda. So, I have placed the point at the 2 lambda and here it is 4 lambda. So, this circle is the 4 lambda here. Now, you can see that there is a difference of 2 lambda and 4 lambda, which is equal to 2 lambda. So, let me write it here. On this side we have 2 lambda circle and on this side we have 4 lambda circle. What if I maintain the same difference of this 2 lambda? And if I select the point, let us say 5 lambda and 3 lambda, 6 lambda, 4 lambda and 7 lambda, 5 lambda, you can see the difference between two values is equal to 2 lambda always. So, we have 8 lambda and 6 lambda. So, these 2 points, 5 lambda, 3 lambda intersection, then we have 2 points, then we have 2 more points, 2 more points and ultimately this one. If I join this path like this, it is the hyperbola. The moving object is there and it is receiving the signals from both of these transmitter. If I want to find out location of that moving object at that instant, I need to solve the hyperbola, and that is why this kind of methods which are based on this logic are called hyperbolic navigation methods. Let us say we take another point, 5 lambda from left side and 1 lambda from the second side. There is a difference of 4 lambda. So, let us maintain this difference and write the terms 7 lambda, 3 lambda, 8 lambda and 4 lambda. If I try to plot these points will be like this. So, these 2 points are corresponding to the 6 lambda and 2 lambda circles. These 2 points are intersection of the 7 lambda and 3 lambda circles, and these 2 points are the intersection of 8 lambda and 4 lambda circles. So, if I draw a curve through these points, it is another hyperbola. It is not necessary that we will always have the position of the object on the center line, and hence whenever the object is away from the center line, which happen, we have the hyperbolic navigation relevant and we can use it. So, now you can see here both transmitters are sending the signal at the same time, which means the signals will meet at the center line. However, if one transmitter is sending the signal with slight delay, what will happen? It will meet somewhere on the hyperbolic path. In case of hyperbolic navigation, position is determined by the difference measurement of the signals. Because of the two transmitters, we will not get the correct position. We need to have one more transmitter. Although the demonstration was good enough to show you, but in fact, when we do the calculations, we need to have minimum 3 transmitters. So, minimum we need 3 transmitter stations. If signals are transmitted at the same time, equidistant intersection at the center line are possible. What if the signals are received at the center point? We have the hyperbolic solutions here in this case. Now, we can see that we can measure the difference in time or phase. Same difference defines a hyperbola, and each hyperbola is line of position or LOP, because we are determining the position here. So, each hyperbola represents a constant difference of range from the transmitters. As we go away on the hyperbola from baseline, the gradient of the hyperbola increases. As we see in the two hyperbolas are having different gradients. And as we go away from the center line, accuracy degrades because the spacing between the circles on the hyperbola are increasing. So, that is somehow a disadvantage of the hyperbolic navigation. So, we can say here that we need to have the minimum 2 LOPs. That means, if we have 3 transmitters, I can construct minimum 2 line of positions, and by solving these 2 line of positions, I can find out the position of a point. So, in case of RoRo navigation, we need only 2 transmitters or 2 reference objects on the surface of Earth. Here we need minimum 3. What are the major idea about the navigation methodologies? One is hyperbolic and one is circular. So, in case of circular, we call it RoRo or RoRoRo, depending on the dimensions we use. The position of the vehicle or the moving object is changing, and I need to measure it. If it is away from the design trajectory, I need to put a correction. So, what is required here? I need to measure the position At the same time, I need to calculate the errors also. What is the error in the position? And that will tell whether the moving object is away from the designed course or designed trajectory or not. And if it is away, I need to make some corrections. And the amount of correction will be depending on the amount of error or amount of the ambiguity in the position of the moving object. And that's the logic here about the position update in navigation. So let us look into this aspect. I will give you a simple example. Let us say you have a constant and you want to measure that constant. Let us say distance is a constant between the 2 points and you are measuring that distance using a device. Let us say tape or total station, and you are getting some readings like x1, x2 and so on. So n number of observations you have. We can develop an idea that each and every observation is having some error. And if you remember, we take the mean x bar equal to x1 plus x2 plus x3 and so on up to xn divided by n. Now let us imagine that you have one more data, let us say xn plus 1. So what is the new mean? The new mean will be x1 plus x2 plus x3 and so on up to xn and n plus 1 divided by n plus 1. Here I would like to rewrite this. Let us say that x1 to x2 xn divided by n plus 1 plus xn plus 1 divided by n plus 1 here. You can see here that this term can again be rewritten as x1 plus x2 plus xn divided by n. Again I am multiplying with the n and divided by n plus 1 here. So I hope that this term here and this term are same, and so I am writing the next term xn plus 1 divided by n plus 1. What is this term here? This term is nothing but x bar old into n divided by n plus 1 plus xn plus 1 divided by n plus 1 here. What is the advantage here? What is the magic here? Let us say that x bar new is equal to x bar old, that is old mean, into n divided by n plus 1 plus x n plus 1 divided by n plus 1. I am trying to update old mean by this multiplying factor and by this additional term. That means I am not doing any new calculation. I am just putting this factor multiplying by this one. I am adding it here. So this is completely new observation, and I am updating old mean and I am getting new mean, and that is position update. In case of the position of a point or the distance between the 2 points is not changing dynamically, but it is a good example to understand. Now imagine that the distance between the 2 points is also changing dynamically with time. So I need to measure the time also to estimate how distance is changing, or I can say as an object is moving in the space or air or maybe in the water, I need to measure the time also to find out its updated position using this logic. For the new position update, I will not consider the complete data set. Rather, I will consider only the mean of the old data set, and I will try to update that mean to estimate new position. First of all, whatever data you have collected before, and once you find out the mean, you can ignore this complete data. That means you are saving the memory of your system. Number two, the next time when you do the calculation of updated mean, once you get one more data, what will happen? You are just considering the mean value and the new data only. Let's say this is the equation. Here you are using a new position xn plus 1 and you are using only the mean, not the old data. So you are saving your calculations also. That means calculation time also. So that is the big advantage here. So you got the idea what's the position update. Now I can rewrite x bar new as x bar old plus xn plus 1 minus x bar old divided by n plus 1. So I have rearranged the same equation here. You are updating old mean by this factor. The concept of updation is like that. You are putting some kind of correction to the old mean using the new data, and you are using some kind of multiplying factor or dividing factor, and you are trying to find out new mean. Imagine that you have a situation where you have observed n data and find out x bar old. Now you observe p number of more data. Try to find out what is x bar new. Imagine a dynamic system. In case of dynamic system, let us say there is a point, position is changing dynamically with time. So let me write a state vector which consists of both position and the velocity. So I write like this: state vector at kth position or kth timestamp is the position p, k, and the velocity vk here. What is error? Let us say they are coming from this covariance variance matrix sigma p square, sigma pv, sigma pv, and sigma v square here. So these are the errors, or we can say covariance variance matrix of pk and vk. So using the measurement process, I am introducing some error here. So what next? I want to estimate xk plus 1. So that is pk plus 1 and vk plus 1. I can write from the standard equations, the position is updated from old position plus delta t times speed vk. Delta t is the time difference. So I can write this. Similarly, what about the vk plus 1? There is no update vk, or speed is constant. So how can I write this in the matrix form? Xk plus 1 is state vector. So this is a state vector at time t plus 1 or k plus 1, and this is also state vector at time stamp k, position k. So xk plus 1 is pk plus 1, vk plus 1 here, 1 delta t, 0 1 pk vk. X k plus 1 state vector is some function called phi into x k vector, and this is the phi. Now what is the error that I expect in xk plus 1? The error is calculated by law of error propagation. We know that the error in the kth position is this, and so I expect the error in the kth position as sigma. I can write, let us say k plus 1 is equal to phi sigma phi t at the kth state. So this is phi which is defined at kth step, then it becomes tk here, that is the time difference between tk plus 1 and tk. So using this logic we can find out what will be the error in k plus 1 position, or the position at k plus 1 time stamp. This is the way we keep on updating the position. If errors are higher, what will I do? I will take the small step of the movement. If errors are smaller, I can take a big step in the direction of movement, in the direction of velocity. So this is the way we do the updation in a position, and somehow this logic is related to the Kalman filter. So if someone is more interested in Kalman filter, they can read it themselves. One more thing I would like to tell you: if you try to control a system, what will happen? Because of the control of moving object, some errors from the control parameters will also be introduced. Error will be added to this somewhere here, and that is what we call the process noise. So that process noise will also decide overall error of the position, and based on that you will try to update position. Higher the error, small update in the position; smaller the error, you try to update position at the higher rate. Now let us consider different navigation systems. First of all, there is a dead reckoning system. It consists of speed sensor and heading sensor. Heading sensor could be a compass like magnetic compass, gyroscope or gyro compasses. Now acoustic navigation system. It is used under the water because acoustic waves travel in the water. Now we have long baseline system and short baseline system. So I will explain all these systems very briefly. And then we have the inertial navigation system, which is having accelerometer and gyroscope. Then we have the radio navigation systems, where we have circular as well as hyperbolic systems and instrument landing systems. And then we have satellite navigation system, which are radio navigation system, what we call GNSS or GPS. I would like to tell you, all the radio navigation systems are superseded by the GPS. So LoRa and Omega are no more relevant today. Still, to understand the philosophy, I will discuss. So let us look into the acoustic navigation system. Generally, we use the frequency in this range 5 to 20 kilohertz of the sound waves, and then it has speed sensor as well as heading sensor. Position is determined with respect to the transducers here. Transducers are mounted on a moving structure, and then the time of flight or the phase based measurements are performed. That means, using the speed of the sound, we try to measure the time of travel or sound profile. We assume here that sound profile in the sea water is known. Area of coverage is defined around the transducers or the reflectors. So it is an example of local navigation system. We'll explain you why. What is the accuracy of positioning? Well, it depends on the vehicle net geometry or the GDOP, geometric dilation of precision at a given instant. Errors are small, statistically constant, smaller temporal component but larger spatial component. What's the meaning here? Errors are very small, but their spatial component is bigger compared to the temporal component. With time, errors are not increasing that much, but at a given moment, errors in the space are much larger compared to the temporal component. Moreover, as we see, the errors are consistent, they are not changing much, and that's why we say that statistically constant errors are there. We have two systems, one is called the long baseline system. Let us say there is a sea water here and there is a moving vehicle, and moving vehicle have a transducer here, and that is sending the pulses in all the directions. Let us say there are three receivers, R1, R2 and R3, which are firmly based on the sea bed. As soon as this moving vehicle comes, they will start interacting and they will reflect back the energy like this. So like this and like this. Again, the ship hull or the ship is having receiver also that will receive the reflected energy, and using time of travel or the phase measurement, we can find out the position of the moving vehicle, and that is the long baseline system. Or now we can see here it is nothing but rho system, because it is measuring the distances between the receiving object and the transducer. We have another system called short baseline system. In case of short baseline system, when we send the pulse, azimuth of the pulse is known. So there is a moving direction here, there is a reflecting surface, so it will reflect back the energy. So based on this range and this azimuth angle, we try to find out the location xy at a given time stamp, and that is called the short baseline system. Now we have inertial navigation system, which is completely independent of any transmitter or receiver. So it measures the position, it measures the velocity, and it also measures the attitude or omega phi kappa with respect to 3 axes. So now in case of position, we say that position is longitude, latitude and the depth along the gravity direction. So it basically uses the gyros and accelerometers to sense the motion in inertial reference frame, which is quite independent from any other non-inertial reference frame. And that is why INS is today under use. In case of inertial navigation system, errors accumulate over time. Let us look into another systems. LoRaWAN-C is a system that is used to locate ship vessels or any other object. The transmitters are based on the ground surface, not on the object. So it is example of an hyperbolic navigation system, and it uses the ground waves. That means transmitted pulses are interacting very close to the ground. Electromagnetic signals are transmitted at very low frequencies by the permanent transmitter network, and the operating range is 600 to 1500 nautical miles, or we also write it NM. Absolute accuracy is 463 meter, or I can say close to 500 meters. These accuracies are absolutely fine for the navigation of the big vessels or big aircrafts. Now you can see that repeatable and relative accuracy. If I try to take the repeated observations, accuracy will be improved up to 18 to 90 meter. And one more system called Omega here, and again it is an example of hyperbolic navigation system. It uses the sky waves. Sky waves increase the operating range or the operating distance. It is using the electromagnetic signals in the very low frequency range. Operating range is 5000 nautical miles and accuracy is 2 to 4 nautical miles. Differential omega is also there, like differential GPS. So standard signal received by the airborne unit with differential corrections, and then accuracy goes to the almost 0.2 to 0.3 nautical miles. What about the mobile navigation software? How is it different from the standard map system? In case of mobile system, you have the map at the background, and map is showing some path from the home to a restaurant. If you have palm top devices for the navigation, they will also show you where to turn, where to stop, whether traffic is 2 lane or 1 lane, whether overtake is allowed or not. So all these informations are available, and those informations are to be first collected, and then your navigation software has a provision to upload those information on the background map. That is why the mobile navigation softwares are completely different from the standard maps. If you see what are the applications of navigation, I would like to request you, please go through this paper, and it is well explained that how can you use the GPS navigation to find out some completely unknown places. Let us say you have a satellite image of a certain area, and then you find out there are few points that you want to go and collect for photogrammetry so that you can correct the satellite image. You know that it is a forest area, and in this forest area you would like to go to those points, and forest area is completely unknown place. You try to arrange a map, and map is very old. By the map you will come to know various villages around that forest and various other places. So using the one-to-one correlation between the features drawn in the map as well as the features in this image. So you have to do a lot of homework here, and then during the planning you find out, so this is a particular village, and that is visible in the satellite image also, because there are few settlements, and those settlements are also visible in the map. Now we can correlate it slightly. On the image you have also identified GCPs, that these are the locations I want to acquire from GPS device, let's say DGPS. But the problem is how to reach there. So if you take the map, you will not understand the map easily. But if you take the image, you have clear understanding of the features. So these points are visible both in the image as well as map. So first convert this map from map projection system to WGS84 system. Now you have the coordinates of all these ground control points in WGS84 system. Collect the data of these points from the map, try to put on the image, and try to georeference image using georeferencing process. In that georeferencing process, you will get the coordinates of these points in WGS84 system. These points could be having some error, say 50 meters or so. Now you take your GPS device, feed those coordinates here, and try to navigate from some location, let's say this location, which is near to the forest area. Let us say this could be a railway station, or this could be a bus stop where you try to reach near to the forest, and from this point you will start navigating to reach to these points. Beforehand we know what is the place where I am right now and what's the GCP location. So using these two locations we are deciding the navigation path. Because you have the image, what will happen? Using the image identification or the features you collect from image, you will try to see when you are very close to the point, and GPS device is telling you how close you are to that point. And you know that the error of GCPs that you estimated from the map, let's say it is 50 meters. So GPS is bringing you very close to the point around 50 meter range, and from that 50 meter range now you use your perception and try to find out where the point is exactly located, and that is done with the help of image as well as map, because image has certain features showing you that the particular point is having some features around that in the field, and using that logic, your perception, you will reach to the point. You can read this paper, complete details are there, you can get benefited from this approach. Alright, so here we stop our lecture, And in the next lecture, we are going to conclude all our 35 lectures or the 10 modules, that what we have learned in this course. Moreover, we will also try to find out whether I have solved problems that we have raised in the lecture 1, module 1. All right, thank you.